Okay, let's start, I think. Um, Today with me, we have Sergio Aguilar. Thank you for joining. Thank you for preparing this webinar. Um, so yeah, you can go ahead. And please, if you have any questions, leave them in the comment section. And at the end of the presentation, we will go through them.
Okay, hello. I hope you all can hear me. My name is Sergio Aguilar, and I will be talking to you about this static header compression and fragmentation in LPWANs. Well, I'm a PhD engineer, now working in R&D in Satellite. This is the table of content of our presentation today. First, I will be doing a small introduction, then we will head to the topics of what are the low-powered wide area networks, and a bit why would we need to support IP version 6 for scalability and interoperability, what are the limitations that these networks have, and why they don't support IP version 6 out of the box. Then we will present this static context header compression and fragmentation framework, going through the adaptation of this framework on the different LPWAN technologies, following by a convergence profile and some open source projects, with the conclusions pointing some of the benefits that we can get from CHC. As I say, in this presentation, I will be doing an introduction to the LPWAN characteristics and limitations. Also, I will present why we need the IP version 6 to facilitate interoperability and scalability, followed by an introduction to the static context header compression and fragmentation framework and its compression, decompression, and fragmentation reassembly functionality. Then how this is adapted over several LPWANs, and the LPWAN convergence profile, finishing with the open source projects of CHC and the benefits. So what are LPWANs? LPWANs are wireless networks that are designed for Internet of Things. They are focused on the long range and low power. They are designed to provide long range communication with really low power. So they bring a cost-efficient solution in many areas, so that you can deploy these networks to connect your IoT devices, your sensors in factories, in your farms also. As its name states, it's low-powered wide area networks. So the low power, you can have devices that operate up to 10 years on a single battery charge. Ideal, you can use this in agriculture, in livestock management, and assets tracking. Those are some of the best use cases that LPWAN networks are now being used in. Also, we have wide area. This means that you can cover a large area with one single base station. This provides a cost-efficient connectivity because you don't need to deploy large amount of base stations on the network. And then you have networks. In this case, we present different networks like Sigfox, LoRa and LoRaWAN, and Narrowband IoT. Some of the characteristics of these LPWAN technologies are the low rate. To achieve this low power and battery lifetime of around 10 years in the ideal cases, and depending on the transmission rates and everything, we have a low rate. So you cannot transmit a lot of information, but you can transmit this information through many years. So here we can see where they are located in the different families of wireless networks. Here we have, for example, Wi-Fi with all the families, where you have a lot of speed and power consumption and small distance. Also, we have Bluetooth with a small speed, a small power consumption, and a small distance also. Then we have, for example, 3G, 2G, 4G, where you have a lot of speed, but you have a high power consumption. And in this area, you can find the LPWAN networks, where you have a small speed, transmission speed. You have a small power consumption, but you have a large distance to cover. Most these LP1 networks have a star topology, and they have a small maximum transmission unit size. The MTU is how much size you can transmit in one transmission. So in this case, for example, Sigfox, you can only transmit 12 bytes. That's a really small amount of information, but it's suited for several use cases. Also, in LoRaWAN, for example, depending on the configuration, you can get up to 242 bytes. Most of these technologies don't support IP version 6 out of the box, so you need to do some configuration on a side to actually support IP. They are restricted in duty cycle. This means that you cannot transmit whenever you want. You have to wait sometimes, depending, for example, in Europe, you can only transmit 1% of the time, then you will have to wait 99% of the time. Also, well, as you don't support IP version 6, then you won't support IP-based protocols. Here we have a general LP1 architecture, where on this side we can see the different end devices. For example, now we talk about tracking of different assets through maritime or trains. Also, we see a lot of cases in health, in monitoring different health, also different appliances that are now connected to the internet, or wildlife also, or maintenance, prevention, all of the prevention maintenance, how you gather data. You are involving many of these LP1 technologies to connect your devices, in this case through radio gateways, to the LP1 core network, that is the one that manages the connectivity, and then it will send the messages to the application server, where you will have your IoT application. So why we need IP version 6 over LP1? The problem is that LP1 technologies have problems with scaling. So to solve these problems and interoperability, to solve all the issues in interoperability, IP version 6 was formed. So the idea is to leverage all these already created ecosystem of IP version 6 and IP version 6 protocols over LP1s. However, these IP-based protocols were not designed for LP1s, and there are several challenges that are presented when you want to use this IP version 6 over LP1s. Why do we want to use it? Because IP already provides scalability with a huge address space. Also, it provides security with several different protocols that are widely used and widely adopted, and also provides interoperability, as you can connect with your phone, your different devices to different networks without having to be really wary on what network you are connected to. So what are the limitations? Why we cannot use just IP version 6 over these LP1 technologies? The problem is that IP version 6 has a large has a large header size. In this case, we are talking about 40 bytes. If you can see here, the LP1 technology has a reduced MTU size of 12 bytes, for example, in Sigfox. So you will just need 3 to 4 messages just to transmit the header without transmitting any information. So you are wasting, let's say, resources because you are not actually transmitting the data that you want to transmit. Also, IP version 6 requires you to support 1,280 bytes that you are able to transmit in this MTU, this amount of information. In this case, since you have small frames, you will need to do some kind of fragmentation and reassembly. But this LP1 technologies actually doesn't provide any fragmentation mechanism, at least Sigfox and LoRaWAN. You will have some kind of fragmentation mechanism and a large MTU size in narrowband IoT, for example. Therefore, there have been studies that have proved that existing standards as 6LoWPAN and other compression header standards are insufficient. You will need even more compression of the IP version 6 header. So in many cases, when you have open spectrum like LoRaWAN, and you have a lot of large fragments, this can actually limit the scalability of each radio base. Therefore, a solution was proposed and created by the Internet Engineering Task Force, in this case the IATF, that is called Static Context Header Compression and Fragmentation. In this case, it's pronounced CHIC. This way it's easier to pronounce it. So the solution was this CHIC framework that is based on two things. Well, CHIC is a technology agnostic framework. This means that it's actually not built for any specific technology. It's more agnostic in that sense. It defines a set of rules. In this case, these rules are how the compression, decompression, and fragmentation reassembly is performed. Also, these rules are based on a static context. So that means that this doesn't change on time, and this static context is previously configured or previously shared between the sender and the receiver, in this case the IoT device and the IoT application. So it exploits the predictability of IoT traffic. For example, if you have a smart meter, you know this smart meter IP address, you know the application server IP address. This won't change probably in many years. So therefore, you can compress these IP addresses and not transmit them because you already know. So the idea is that since you can predict the traffic that you have, you try to remove, well, it's a process to actually compress the fields that are not being that are repetitive, or that you can find patterns on them that you don't need to transfer. So here we will have for example, the application payload, for example, an IP version 6 packet that is compressed. If no fragmentation is needed, this means that once you apply compression, you are able to transmit the information in one frame. You can transmit it in already. Else, you will need to do some fragmentation. Depending on the mode, you will have some ACKs and retransmissions. And then on this other side, you are able to reconstruct the data that was sent in the sense that the header is the one that is compressed. Here we have a bit more explanation of the header compression. Here in the picture, we have the IP version 6 header. This header is compressed into a rule ID. This rule ID helps identify this context and these rules that are the ones used to compress this specific packet. If you cannot compress all fields, because some fields are different and you need to send these fields always, then you will have this compression residue. So this is really a tailored way to compress the IP version 6 header, because if you cannot find a rule that can compress the complete packet, you can also send a compression residue. So this is really good. Also, based on this compression is based on operators like equal, ignore. If I ignore a field, that means that I don't need to send it. If the field is equal, I don't need to send it. So they are based on operations and some you need to take the decisions. On the other side, we have the fragmentation reassembly. In this case, CHIC proposed 3 fragmentation modes that provides different reliability and performance. In this case, for example, we have the CHIC packet. We perform fragmentation, and we have little pieces of the CHIC packet that are called tiles. So each tile is numbered with a fragment compressed number, and you will group several tiles into a window. In this example, we have 7 tiles in window 0, and well, in this case, we only have 1, 2, 3, 4, 5 tiles in window 1. In this case, the last tile is identified with a special number to signal the end of the packet. So there are 3 fragmentation modes. We have one that is called no ACK mode. In this case, as the name states, you don't have ACKs, so there is no feedback between the sender and the receiver. This is useful when you have devices, IoT devices, that are only uplink, that are only sending data and are not expected to receive data. Actually, in some LP1 technologies, you can have devices without the receiving radio. They only have the transmission radio, depending on the protocols that are being used. For example, this is the case for Sigfox devices. Also, you don't support, in this case, you don't support out of sequence delivery. All message needs to be in sequence of how you send them, but you support variable MTBU sizes. For example, in LoRaWAN, you can have, with the adaptive data rate, you can have changes on the frame size on the MTU on the fly. So this way you are able to adapt to these changes. Similarly, you can have tiles that are of different sizes. Here we have some example of a transmission using NOAC mode, and also we have an example of the regular and all one chick fragment, just as an example. Here, other mode that is present on chick is called always mode. In this case, this mode provides reliability by means of retransmissions. This means that you have a guarantee that the packet will be delivered. Obviously, if you don't have any timeouts. It is window based, as we saw before on the previously fragmentation reassembly slide. We have windows, so we classify the tiles are groups in windows. And these windows, in the case of ACK always, you will always have an ACK at the end of a window. It doesn't matter if the ACK is positive or negative, you will always be having an ACK. And the packages, in this case, the tiles need to be in order when are received by the receiver. In this case, we have also an example where we have three tiles. Let's say a chick packet that has three tiles. So here we have an ACK OK of the first window. Well, in the first window, we have three tiles. Then we have three tiles more on the second window. And here we have an ACK OK that completes the transmission. Here we only have actually the three tiles, but we have one that is lost. So there will be a feedback, and the sender will be notified that this tile is missing. So it will perform a retransmission, and at the end you will have an ACK signaling that all the process has been completed correctly. Finally, the third mode of chick fragmentation reassembly is the ACK on error mode. The ACK on error mode is a mode that only sends ACKs when you have errors, like its name states. So the idea is that you can send several windows, and only windows that have errors will have ACKs. Now this mode has been updated with a compound ACK that provides that you can actually group the errors of several windows on a single ACK. In this case, we have one error, in this case in window 2, and we will have the retransmission of this frame with all the corresponding tiles, and then we will have an ACK success. As you can see in this other example, where we don't have losses, we only have one ACK at the end of the transmission. In this case, to guarantee that all that transmission has been performed successfully. So what does chick provides? In this case, chick provides an IP version 6 compression and decompression mechanism. This was built to tackle the large IP version 6 header size. As we saw before, that was one of the challenges that was present. Then it also provides 3 fragmentation reassembly modes. These were made to tackle the large MTU size requirement of IP version 6. So by using chick, you are able to tackle these two challenges and actually use chick over different LP1s. But the work of the LP1 working group of the IETF in this case moved forward, and they actually built customized standards so that you can actually optimally adapt chick to different LP1s. So now we have the chick over Sigfox profile, the chick over LoRaWAN profile, and the chick over narrowband IoT profile that have been standardized by the IETF. Here, a small overview of the chick over LoRaWAN profile. In this case, this profile provides fragmentation reassembly modes for uplink and downlink fragmentation. It also provides retransmissions and variable NTU change management. So in case you need to only have retransmission on your LoRa network, for example, on your LoRaWAN network, I'm sorry, you can use CHIC, and this will manage if you have also the adaptive data rate. So you will be using a standardized framework instead of probably trying to build your own solution. As you can see here, CHIC compression decompress fragmentation, in this case, is hosted on the end device. And then after going through the LoRaWAN gateway and the LoRaWAN network server, you will have the compression and reassembly. Then the packet is injected into the IP network, and you can have the IoT application with all the stack of IP using, for example, UDP, using another protocols like CoAP, or specialized protocols for smart meters also are supported. Actually, CHIC has been adopted by the LoRa Alliance as the way to support IP version 6 in LoRa networks. Also, we have the CHIC over Sigfox profile. In this case, it provides different fragmentation reassembly modes depending on the packet size. So if you need to transmit large packet sizes on the Sigfox network, or also provide reassembly, reliability, you can use this CHIC over Sigfox profile. In this case, you will have the Sigfox network, and also you will have this CHIC compression fragmentation. And after the network server, when you go out of the Sigfox cloud, you can have the compression reassembly, and then you can inject also the packet to the IP network. So you can also have your IP version 6 hosted applications. In the case of CHIC over narrowband IoT, in this case, it's been tested and it's been tailored for non-IP data delivery, for example. In this case, since you compress the IP headers, you don't need to have there the IP information. So in this case, you can do some application compression, and you don't need to modify any, for example, of the 3GPP architecture. According to some studies that were performed, in this case, this study showed that there was a 64% gain when using, for example, DTLS, UDP, IP version 6, and CHIC, compared to a standard DTLS, UDP, IP version 4, and also a 74% gain when using DTLS, UDP, IP version 6 with CHIC over narrow over non-IP data delivery. In the first case, I'm sorry, in the first case it's 64% if you are using the IP communication of the mobile network. In the other case is in case you are using non-IP data delivery. So as you can see, in this case, there is a lot of gain that you can have when using CHIC over narrowband IoT. For example, when you go beyond the landscape of terrestrial networks and you go to non-terrestrial networks, for example, using narrowband IoT and a standardized solution of 5G, to actually have less data on the channel is beneficial not only for the network that is optimized, but also for the application, as the device needs to transmit less information using less the radio, and at the end having a larger battery lifetime. So we have seen these three different profiles of CHIC, over LoRaWAN, over Sigfox, and over narrowband IoT. And finally, we saw that there is a trend also, that is the LPWAN technology convergence. That is actually a trend that has been identified by IoT analytics. And there is a proposal of using CHIC as in a convergence profile to unify the different CHIC profiles and use just one. In this case, this study was performed, and there were identified a lot of similarities between the different profiles of the different LPWAN technologies. So the idea is to reduce the code complexity and maintenance, and achieve a single convergence, in this case, the chip fragmentation reassembly sublayer, but also to provide a single code base for different LPWAN networks. Why this can be useful? Well, when you have multi-radio devices, for example, nowadays more and more multi-radio devices have appeared. Also, when you have multi-network applications, when you need to migrate one application from one IoT, from one LP1 technology to another, it's easier to have a single code base, a single server code base. Also, we see it in network redundancy. For example, if you have any LP1 technology, then and you go out of coverage, for example, you can have the satellite there, also providing, in this case, narrowband IoT coverage, and you can have these seamless transmissions between the network. Also, for example, you can also have a backup network. You can actually test the performance of one network in another network. You can also increase duty cycle as you have more networks available. There are several use cases, and more multi-radio devices have appeared each day. Now going into the conclusions, there are several open source projects. If you are interested in going into the details of the implementation of CHIC, in this case, we have OpenCHIC. That is one of the largest projects. It's an implementation on Python and MicroPython in all versions. We also have the CHIC over Sigfox project, where you have all the server side and device side implementation. And there is this new initiative that, well, I have started also, that is called CHICduino, that is to provide an open source implementation of CHIC for Arduino. This implementation is focused on this CHIC convergence profile to provide a single code base that can be used on several Arduinos with different LP1 radios. So the idea is that you can facilitate the integration and migration of multi-radio application and multi-network application and multi-radio devices. Finally, one of the benefits that have been shown also of CHIC is that you can have actually a benefit of 7 more times devices per cell. Also, that the energy consumption on the device side can be reduced between a 30 and a 70%. And also that depending on the amount of data that is being sent and the headers predictability of the header, you can have between 40 and 90% reduction in the data that is being sent. Remember that all this energy consumption and data send is tied together. As less data you send, a higher reduction in an increase in battery lifetime, because you have a reduction in energy consumption. Finally, going into the conclusions of the webinar of today, we saw that LP1s are limited in the MTU, and for example, the ones that use open spectrum can be limited in scalability. If you begin sending large packages on a LoRaWAN network, for example, you can have problems. Also, if you have reliability on the downlink traffic in LoRaWAN, you can also have issues because of the scalability of the network. So the use of IP help us, in this case, IP version 6, help us solve interoperability problems between networks. Because, for example, once you are on the IP network, you can connect many things, and you can also manage the scalability. You are able to manage these devices. For example, you have protocols like CoAP or lightweight M2M that will help you manage this scalability and the interoperability of different networks that you are managing. But for that, you need IP version 6. And for that, you need to adapt IP version 6. So IP version 6 is not designed for LP1s and needed an adaptation. In that case, CHIC appears as a solution to provide this IP version 6 header compression and also fragmentation. So these reductions of the IP headers helps with scalability, because you send less data across less data is sent, so you help also the overall network performance. And remember, always, less data that you send, you have less energy consumption that will be reflected in a higher battery lifetime. Finally, the specification parameterization of SCHC over each LP1 technology. We presented how it was parameterized, or at least a bit of the information of how the architecture are mapped between the SCHC architecture and the LP1 network architecture, and also how the SCHC convergence profile can help also in the issues of interoperability and simplified code development. Thank you very much, and any questions that you have.
Thank you for
Yes.
your presentation. Yeah, as you said, please leave comments, questions in the chat. And in the meanwhile, I do have one question. Could you expand on how can all this be applied to non-terrestrial networks specifically?
Yes, of course. In case of non-terrestrial networks, for example, you actually have this time that can be sent where you can see the window of time where you can see the satellite. So actually you can adapt for example, the tiles and windows so that you can have reliable communication over this period of windows of time. So still some you can parameterize still a bit more this SCHC framework so that you can have reliability over these non-terrestrial links. For example, if you're using narrowband IoT, for example, so in this period of time, you can send IP version 6 compressed packages, for example, using lightweight M2M. So instead of having large payloads that you are sending, you are actually cutting different parts of the protocols. Actually not cutting, compressing is the right word. You compress different parts of the protocols. For example, you can compress the COAP header, you can compress the UDP header, you can compress the IP version 6 header. So you can compress different headers on different parts. Also, you can compress before security and after security. After applying the TLS or TLS or any other OSCORE or any other special security protocols. So this way you are able to send the less amount of data over the link. This will allow your device, your non-terrestrial device, for example, that is working with satellite communication, to actually improve its battery lifetime.
Thank you so much. So yeah, I think we are finished. Please keep on connected to the NTN IoT community. We will be organizing future webinars that we hope interest you. So Sergio, you want to say anything else?
No, thank you all for your time, and hope you got interested in SCHC, header compression and fragmentation, and any other questions, you can drop me an email anytime.
Or you can also ask the questions on the post of the webinar.
Of
It will be
course.
automatically posted, so you can just drop your questions there, and we will answer them.
Or in the community also.
Yeah, exactly, in the community. So thank you, and see you next time.
Thank you.